All right, so we're in 15.8 now. In 15.7, we discussed an alternate coordinate system that in some cases made it easier to evaluate certain triple integrals. There's one more coordinate system that we want to look at for that same purpose. These are called spherical coordinates. So here's the idea behind spherical coordinates. Suppose we have a point in 3 space. In rectangular coordinates, we would say that it has coordinates x, y, z. Rather than look at the coordinates relative to its position along the x, y, and z axis, what we do is we come up with a system like this. So this first value here, rho, represents the distance between the point and the origin. This is different from r in cylindrical coordinates. R was the distance between the projection of that point into the xy plane to the origin. So that would be like this length right here, but we're looking at this length right here. The other two coordinates that we use, theta and phi, are both angles. And the angles, one of them measures the angle between this line segment that we got our measurement for rho from, so the line segment joining the point to the origin. We measure it from the positive z-axis to that line segment. Theta is the same theta that we would be using in cylindrical coordinates. So by theta, what we mean is if we were to project this point into the xy plane and then connect the origin to that point with a line segment, theta measures the angle between the positive x-axis and that line segment. It's the same exact theta as in cylindrical coordinates, which is why we use the same label for it. Now, there's a couple of restrictions we put on both rho and phi, which you're seeing right here. Rho, we're going to assume, is a non-negative number. So we think of it as a true distance. This differs from things like polar coordinates or cylindrical coordinates, which generalize polar coordinates, where r can actually be a negative value, and we just have an interpretation for what it means when r is negative. In spherical coordinates, this distance phi is never negative. So we don't have to think about, an alternate interpretation for that. Phi also is restricted to lying between 0 and pi, so 0 and 180 degrees essentially. And the reason for that is because regardless of where this point is, I can always describe its angle from the positive z-axis as a number between 0 and pi. Notice if I were to take this point and keep both rho and theta the same and just sort of move the point by changing phi. Once I get to that negative z-axis, there's no need to go beyond pi, because if that point ends up over here, then I can keep phi between 0 and pi and just adjust my theta accordingly. I can have theta swing around because there's no restrictions that we put on theta. So these restrictions are sufficient to describe any point in 3 space using spherical coordinates. And that's useful because it turns out that these restrictions actually make the conversion between the two coordinate systems easier to manage. So just as we do anytime we introduce a new coordinate system, we want to look at what some of the simplest types of functions look like when we graph them in this new coordinate system. In particular, we want to look at constant functions. So if rho is a constant, rho equals c, then phi and theta are free to vary. And basically, we're just looking at the set of all points that are a distance of c from the origin, since that's what rho represents. We know that's the definition of a sphere of radius c. And this is the reason why we call these spherical coordinates. Spheres, which normally have, we work with them a lot, but they normally have kind of a cumbersome representation, or a cumbersome equation in rectangular coordinates. They're very, very easy to describe in spherical coordinates, as you would expect. If we let theta equal a constant, but we let phi and rho vary, then basically we're just looking at the set of all points whose projection into the xy plane are going to have an angle of c with that positive x-axis. What that creates is what we call a half plane. And again, remember, because rho is not allowed to be negative, we don't use points that are on the opposite side of z. We don't have an entire plane that goes both directions, because that would imply that, you know, we have rho interpreted as a negative number, which takes these points to the other side of this z-axis over here. So it's called a half plane, and it looks like this. Finally, phi equals c. If we have the constant function phi equals c, that creates a half cone. If you remember back when we talked about quadric surfaces, mathematically speaking, in this context, a cone actually has two parts to it. It has the part that opens upward and a part that opens downward if that cone is symmetric about the z-axis. However, if phi is equal to a constant, that's only going to give us a half cone. And you can visualize that here. If I hold phi constant, but I allow rho to vary, then this point can move along this line segment, or the line passing through this, and go as far as it wants to. And then if theta is free to vary, that point can swing around in a circle centered at the z-axis. That creates this cone down here. If c is a value between pi over 2 and pi, notice the way that we define phi. If that angle is more than pi over 2, that's going to bring it through the xy plane and put it below the xy plane. So our cone would look like this in that case. But these are what constant functions look like in spherical coordinates. Okay, now let's look at converting between rectangular and spherical. So right here, I have the same figure that I had drawn up above, or that I had shown up above, with a little bit more detail. Everything in blue is here to compare rectangular coordinates to the red, which is given in spherical coordinates. So there's a couple of values that we need which come from cylindrical coordinates that we use to kind of bridge the gap between these two coordinate systems. First of all, remember, if I were to project this point P into the xy plane, I'm going to call the projection P prime. And notice in rectangular coordinates it would have coordinates x, y, 0. R, which is a value that we use in cylindrical coordinates, will represent the distance between the origin and that point P prime. Notice that because this distance was drawn perpendicular to the xy plane, that's what a projection does. It creates this right triangle right here. Okay. Also, you see that phi appears here because that's how we defined it, but it also appears here in this right triangle. That's because these two angles are alternate interior angles. And from geometry, we know that they're congruent. So this would also have to have the same angle measure as this. Putting some of these things together, notice first of all, z in rectangular coordinates, which would represent the height or altitude of this right triangle, can be put in relation to these other angles and sides here using some trigonometry. So you can see this little formula right here. In fact, I'll put my z here as well. So cosine of phi would be adjacent over hypotenuse, z over rho. What if I solve that for z? Z is equal to rho cosine of phi. So there's a connection between z and some of the values that we have in spherical coordinates. R has a similar relationship. R is the opposite side from phi. So a similar derivation would give us R equals rho sine of phi. Okay. Now, how do we relate this back to the x and y coordinates? Well, excuse me. Looking at our x and our y here, we see that this would also create a right triangle. And in this right triangle, the angle theta is given, and the side length r is the hypotenuse of that right triangle. So I know that if I want to get an expression for x, really this is like looking at this kind of in polar coordinates. So from polar coordinates, I know that x is equal to r cosine of theta, and y is equal to r sine of theta. However, if I take this expression and use it as a substitution for r in each of these expressions, I get the first two conversion formulas that I see down here. And since we already came up with one for z, this gives us a complete set of conversion formulas that can get us from spherical coordinates to rectangular coordinates. It looks a little bit more complicated, but we have x equals rho sine of phi cosine of theta, y equals rho sine of phi sine of theta, and z equals rho cosine of phi. Similarly, from this diagram as well, we can also get this little useful conversion formula, giving us rho squared equals x squared plus y squared plus z squared. That simply comes from the fact that rho is the distance between the origin and the point x, y, z. So that's pretty automatic. Okay. All right. Oh, I actually skipped my example down here. Didn't mean to do that. So we want to do a couple of examples where we just work within this coordinate system, getting used to it without having to do any integration quite yet. I want to start by plotting this point, 2 pi over 2 pi over 4. So let me create my coordinate axes first. Okay. All right. So what I'm going to do is create a diagram similar to really this one right here. So I'm actually going to draw in as a guide some sort of a right triangle. Let's start by looking at the angle theta, actually. So remember, theta is the coordinate in the middle, pi over 2. Theta being pi over 2 means that I want to create an angle that's pi over 2 radians, or 90 degrees, from my x-axis. Notice that takes me to the positive y-axis. Okay, and then what I want is an angle of phi, so I'm going to look at the third coordinate next, measured from the positive z-axis over this positive y-axis where we just ended up. Okay, and I'm going to actually label that. That's pi over 4 right there. Finally, the point is going to be on that line segment 2 units from the origin. So rather than try to figure out, what would be the coordinate, or what would be the labels on my axes to make sure that I get this length to be 2, I'm just going to label the line segment as 2, just to indicate that that's what that length is. Now I could use these conversion formulas to determine, what would y and z and x all be for this point, but I'm not going to bother with that. Okay. Next up, let's look at a conversion from rectangular to spherical coordinates. So this is a point that's given in rectangular coordinates. Excuse me. So what we want to do is use some of the things that we know about how to convert between points. The first thing that's going to be reasonable to find is rho. So remember, rho squared is equal to x squared plus y squared plus z squared. That's 1 squared plus 0 squared plus root 3 squared, or this would just come out to 4. This implies that rho is equal to 2. Not plus or minus 2. Remember, rho is strictly defined to be a non-negative number, so we don't have to bother with pluses and minuses here. Okay. Now we need phi and we need theta. So if you go back to the conversion formulas that we derived over here, the ones for x and y need us to already know both phi and theta, but z only requires us to know rho and phi. So here, this would be the only unknown in that equation. That's something that I can solve for. So z, which is root 3, is equal to rho, which we just found to be 2, cosine of phi. Or cosine of phi is equal to root 3 over 2. Okay? I know that this would have solutions in the first and fourth quadrants if I was treating this like just a regular trigonometric equation that I wanted to solve. However, remember we have a restriction on phi. It has to lie between 0 and pi. That means that the solution that I want from this is the only solution that lives in the first quadrant. So this implies that phi is equal to pi over 6. Okay, And now we have two of the three things that we need for spherical coordinates. So going back to my conversion formulas one more time, I can use either x or y, either of these conversion formulas to try and find theta next. It doesn't really matter which one we use. Let's use x. So x is equal to rho, which we know, times sine of phi, we know phi now, cosine of theta. Theta is what we're trying to find. Okay, so y, I said x, which is 1, is equal to rho, which is 2, sine of phi, sine of pi over 6, cosine of theta. Okay, well, sine of pi over 6 is 1/2 times 2, that would be 1, and so this implies that 1 is equal to cosine of theta. And then solving this for theta. Now there are no restrictions on theta, so this will have more than one solution, but the first one that comes to mind is theta equals 0. Then of course I could use theta equals 2 pi, theta equals 4 pi, but because those are all coterminal angles, none of them are going to give me a different point. So I'm kind of free to use any of them. Let's just use 0 since that's the simplest. So in spherical coordinates, we would have 2, 0, pi over 6. And again, remember, the order that we put these in is rho, theta, and phi. Okay? In the next video, we'll talk about how to do triple integrals using spherical coordinates.